In section 2.1, we talked about the first derivative test, which allowed us to see when a function was increasing, when a function was decreasing, and to determine the local maximum and the local minimum. In this section, we will talk about the second derivative test. So suppose that f is a function whose derivative f prime exists at every point in an open interval I. F is called concave up if f prime is increasing over I. We'll talk about this when we look at the graph. So remember f prime, this represents the slopes of the tangent lines. So f is concave up if the slopes of the tangent lines are increasing. Let me show you guys what that looks like. Let's take this point over here, and you know what? Let me pick up a different color. Let's take this point right there, and this point has the tangent line has a negative slope. And then look what happens slowly as we get over here. The slope goes from being negative to 0. And then from here, the slopes go from 0 to being positive. So the slopes are going from negative to 0 to positive, so the slopes are increasing. So the function f is concave up when the slopes of the tangent line are increasing. They're going from negative to 0 to positive. On the other hand, f is concave down if f prime is decreasing. So remember, f prime, these are slopes of tangent lines. So the slopes of the tangent lines are decreasing over some interval. So let's take a look at what concave down looks like. So in concave down, if I take this point, it has the tangent line has a positive slope. Over here, the tangent line has a 0 slope. So we went from positive to 0, and then over here, the tangent line has a negative slope. So what's happening here is the slopes of the tangent lines, these are decreasing on that interval. And the point at which the concavity changes from up to down or down to up, this is called an inflection point. All right, now let me show you guys kind of an easy way to figure out if the graph is concave up or concave down. If the graph is making a U shape, in other words, if at any given point the tangent line is below the graph, below the graph, below the graph, then this is called concave up. So concave up is anything that has a U shape or any part of a U shape. This is an inflection point because look what happens at this point right there, the U turns upside down. So if you take any point in this interval, the slope of the tangent line or the tangent line will actually be above it, not below it. This is part of like an M shape. So anytime you have some kind of an M shape or part of an M shape, this is considered concave down. So concave up, the slopes of the tangent lines are increasing. They go from negative to 0 to positive. When you have concave down, the slopes of the tangent lines are decreasing. So they go from, so the function goes from increasing to decreasing. So the slopes are going from positive to 0 to negative. Concave up U shape, concave down M shape. Let's take a look at some examples of this. Here, this function has a U shape up to this point, so this is concave up. Over here, this is like an M shape, so it's concave down. Once again, we have a U shape, so it's concave up. Let's look at what's happening to the slopes. Slope of the tangent line is negative, slope of the tangent line is 0, slope of the tangent line is positive. So the slopes are going from negative to 0 to positive, slopes are increasing. Over here, the slope of the tangent line is positive, this is 0, this is negative. So we're going from positive to 0 to negative. Since the slopes are decreasing, this is concave down. Over here, the slope of the tangent line is negative, this is 0, this is positive. So we're going from negative to 0 to positive, which means the slopes are increasing, and this is concave up. Another example, we have a U shape, so this is concave up. Over here, the U changes to an M, like it kind of turns upside down. So this is going to be concave down, and this point, this becomes a U again, that's concave up. This point becomes an M again, so it's concave down. So this is concave up, concave down. This is an M part of an M, this is part of a U, part of an M. So this is when you got a U shape, this is concave up. We have M or part of an M, like this is like the like the second half of the M. This thing, so this is concave down. This is concave down and increasing, concave down and decreasing. All right, here's a quick example. Determine over which interval or intervals the functions graph below are concave up and concave down. So remember, concave up, it means we're looking for a U shape. So this is part of a U shape, part of a U shape, up until approximately this point. And for now, we're just going to approximate visually. Later on, we'll be doing this using calculus. So concave up is going to be this interval over here. This is a U shape, but at about this point, the U turns into an M shape. So then this is going to be concave down. This interval, M shape, M shape, M shape. This is going to be concave down. But look at what happens like right there. At that point, the M shape once again changes part of a U shape. So this once again is going to be concave up. So over this interval from -infinity to -1, the graph is a U shape or concave up. Also from this interval 2 to infinity, the graph is also a U shape, so this is concave up. This middle part is an M shape. So from -1 up until +2, this is concave down because the slopes are going from positive to 0 to negative. Slopes are decreasing, so this is concave down. And again, another really quick way to look is if this tangent line is above, this is concave down. If the tangent line is below the graph, it's going to be concave up. So concave down between -1 and +2. Let's take a look at another example. So we have a U shape, 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 all the way up until about this point. And notice the U changes to an M shape. So in this interval from like -infinity until 0, this is going to be concave up. And then when x equals to 0, this the shape changes from a U shape to an M shape. So this is going to be concave down till about right there. And then at about that point, we change the graph from concave down to concave up because the graph changes to a U shape. So we're going to be concave up between -infinity and 0 in that interval, and also from the interval of, this is like x equals 2, from 2 to infinity. We're going to be concave down between these x values, which is from 0 to 2. Okay, now we want to, when you talk about increasing and decreasing, this is not about concave up, concave down. That's just when the graph is decreasing, so the y values are going down. So the graph is decreasing, so this is the graph is increasing, it starts decreasing here in between x equals -1 and x equals +2. So in this interval, the graph is decreasing. So it's decreasing when the x values are between -1 and +2. Now the point of inflection, so now this is concave down. Now we're looking at concavity. So this is concave down, because this is an M shape. And then like right about there, the M shape changes to like a U shape. So at about x equals 1, it goes from concave down to concave up. But this is kind of hard to determine, right? Like, how do we know that's the exact point? Because we don't want to approximate, we're going to be using calculus to find the points of inflection and to determine concavity. So here's a theorem. This is a test for concavity. If the second derivative is greater than 0, then on that interval, the graph is concave up. If the second derivative is less than 0 on that interval, then the graph is concave down. Okay, second derivative greater than 0, concave up, second derivative less than 0, concave down. So here's a quick summary. If you want to determine if f of x is increasing or decreasing, so it just literally like is a function going up or is a function going down, then we would use the first derivative. If you want to determine if f of x is concave up or concave down, that's when you would use the second derivative. So first derivative is to determine if a function is increasing or decreasing. Second derivative is used to determine concavity, if it's concave up or concave down. Here's an example. Let f of x equals to 2x squared minus 3x plus 1. Find f double prime of x. So first, let's just find f prime of x. Multiply 2 times 2, this gives you 4x minus 3. F double prime of x, which means we take the derivative of the f prime of x to get the second derivative. So this is like a 1. 1 times 4 is 4. This becomes 1. So the second derivative is just equal to 4. It's a constant. Then we want to evaluate, this is the second derivative. We want to evaluate the second derivative at x equals to 2. So when you have a constant function, no matter what the input is, your output is always going to be 4. So the second derivative is going to be 4. Now, what does this say? If the second derivative is positive, then at that point, the graph is going to be concave up. And because f prime of x will always be positive, there's no variable there, so it's a constant, it's constantly going to be positive, this entire graph is going to be concave up. So this whole graph is a U shape, which means this entire graph is concave up, and it's never going to be concave down. Let's take a look at another example. Oh, so, another theorem, sorry. So let's say that f is differentiable, which means we can take the derivative for every x in an open interval. Then, and there's a critical value at which f prime c equal to 0. Remember, critical value, this is a turning point. So let's say we have a turning point in an interval. Critical value, there are two conditions. Either the first derivative has to be 0 or the first derivative is undefined. So if a critical value exists, which means the first derivative is 0 or undefined, which means we have a turning point, then we can just use the first derivative, we can use the second derivative test to determine if that critical value is a local maximum or local minimum. So here's what it's saying. Here's what the theorem says. That critical value is a local minimum if f double prime of c is greater than 0, which means it's concave up. Now let's think about concave up. Concave up is a U shape. So if you have a U shape, that means we're going to get a local minimum. So it's a relative minimum if f double prime of c is greater than 0, which would make this concave up. Function is concave up, then that critical value or critical point is going to be the local minimum. The critical value is a relative maximum or local maximum if the second derivative is less than 0. So less than 0, this means it's going to be concave down. Now what does concave down look like? It looks like an M shape. So for that, this point is going to be a relative maximum. So if it's concave up, which means second derivative is greater than 0, that critical value is a local minimum. Concave down, it's a local maximum. Okay, so here's an example of that. This is a critical value. This critical value, this is part of a concave down because the graph is part of an M shape. So this one is going to be a local maximum. Whenever it's concave down, we have a local maximum. This point right here, this interval is part of a U shape. This is concave up. So when we have concave up, this is going to be a local minimum. Same thing over here. We got concave up, which means this is going to be a local minimum.